Hello everyone and welcome to Fatal Sec. As AI evolves, it's changing the way we analyze and reverse engineer apps and binaries. To stay ahead, we need to master AI powered tools while understanding their limitations. So in this video, I will show you how we can leverage AI to decompile binaries and transform them into high level code like Swift, Java or C. Let's dive in. To demonstrate this, I have created this simple authenticator program. Let's see it in action first. /authenticator, and as soon as we launch the program, it prompts us to enter a password. Since we don't know the correct password yet, let's just type in something random like I don't know and hit enter. As expected, the program responded with access denied message. Okay, before getting started with the AI powered analysis, we have to set up few things. Firstly, because we are going to use Radare 2 disassembler, make sure that Radare is installed. So I am going to set up everything with you guys step by step so that you can follow along. And I usually set up my tools under documents directory. So let me just switch over to documents in another tab. And now in order to install Radare 2 disassembler, you can simply clone this repository by copying this git URL and then put git clone followed by the repository's URL. Enter. It's now cloning into this Radare 2 directory. And once the cloning is done, you can install it using radare 2/sys/install.sh script. Enter. This is going to take some time, so please be patient. I am going to speed up this process. The reason why I am showing you this installation process is because in case if any error comes up during the build process, we can then troubleshoot it together. Alright, so now Radare 2 is installed. You can confirm this by typing R2 command in your terminal, and if you get this usage, it means that R2 or Radare 2 is installed properly. Next, we need to install R2 Ghidra decompiler, which we will use later on to analyze this binary. To install R2 Ghidra, we can simply use package manager of Radare. Let me just clear out this terminal, and now to install R2 Ghidra, we can simply use package manager of Radare using r2pm-ci, then followed by the plugin name, which in this case is R2 Ghidra. Enter. This is now going to clone the Ghidra decompiler, which we can then use in Radare's disassembler to decompile the code. Again, it's going to take some time for building, so I'm going to speed up this process. The reason why we are installing R2 Ghidra is just to show you the difference between the code which is being decompiled by traditional decompilers like Ghidra versus the decompiled code which is generated by an AI assisted decompiler. Okay, so R2 Ghidra is now finally installed. Let me just clear out the terminal once again. So with that installed, it's time to level up our toolkit by adding AI powered capabilities to the Radare 2 disassembler. We're gonna need two plugins which are going to enable AI support. Since we already know that Radare 2 plugins can be installed using the R2PM package manager, let's put it to use and install these game-changing plugins. R2PM-UCI. First plugin is called R2AI, which is responsible for integrating AI assisted analysis into Radare 2 workflow. And then the second plugin is called DecAI, which is an AI assisted decompiler that transforms low level assembly into readable high level code. So here it's cloning R2 AI plugin. Make sure that you have Python virtual environment installed, otherwise it will throw error at this stage. I already have it installed on my machine. Again, it's going to take some time, so I'm going to speed up this process. Okay, so R2 AI and Deck AI both are installed now. Don't worry if it's not clear what these two plugins are. They will make more sense later on when we actually use these plugins. Again, let's just clear out the terminal. Alright, now we have reached the final and most powerful piece of our setup. Can you guess what it is? If you have ever wondered how AI powered tools work, the answer lies in LLMs, large language models. These models are trained on massive datasets, allowing them to understand and generate human like code and text. The real magic behind any AI driven tool comes from the quality of the model it uses. A stronger, more refined model means better predictions, smarter analysis, and more efficient decompilation. So before we dive into action, let's install this AI powerhouse to supercharge our reverse engineering workflow. For that, I am going to launch R2 AI prompt in interactive mode using R2PM-R followed by R2 AI plugin. Enter. As you can see now, we are into R2 AI prompt. Now using hyphen capital M option, we can list down all the available models that R2 AI supports. Apart from these remote models, all other models can be downloaded locally and seamlessly integrated with Radare 2. But before we proceed, let's take a moment to pause and strategize. The key question is, what's your use case? Choosing the right model depends on your specific needs. Since our goal is to analyze code and disassemble instructions, we should focus on models that include code or instruct in their names, as they are specifically designed and trained for tasks like reverse engineering, decompilation, and static analysis. Let's pick the best model for the job and unlock the true power of AI driven disassembly. So for now, I have decided to go with second option, which is Quant Factory Granite 8B Code Instruct. This model is developed and trained by IBM. Here, this 8B signifies that the model has 8 billion parameters, which is a key factor in its performance and accuracy. Generally, more parameters means better accuracy and deeper analysis. But there's a catch. It also demands more computational power and resources. So, when selecting a model, it's essential to strike the right balance between capability and efficiency based on your available hardware. Okay, so this being said, let's select this model, for which all you have to do is copy this command and paste it in R2AI prompt, hit enter. And then we have to tell R2AI to download this model. And for this, the simplest way is to simply ask it as a query. So here we can simply ask R2AI to download this model for us. Enter. Okay, so the reason why I got this exception is because I have already another model installed and configured, and it basically tries to look for this new model which I am trying to download now. So here in this path, it basically throwing this exception that the model is not found. So you can simply ignore this message. It will then show you option to select the type of the model. Now, depending on your system's configurations, you can either go with the large model, or if you don't have high powered system like me, just go with the small one. Okay, by default, small is selected. So let's just hit enter. And now it's showing you various options which are available in the small sized category of the model. So along with each model, you can see the size and also the estimated RAM usage. So based on this RAM usage, you can decide which model to download. If you have a good configuration, go with higher sized model. Based on my system's configuration, I am choosing the third one, which is Q3KM, which is of size 3.7 GB and it's gonna take RAM of 6.2 GB. So let's select this, hit enter. Now it's asking you whether you want to use this model by default or not. So let's just say yes. And now it's showing you the directory where the model is going to be downloaded, which in my case is under this directory. Let's leave it as it is, hit enter. And now it's gonna start downloading the model. Now, depending on your internet speed, it's gonna take some time. So I'm gonna speed up this process once again. Okay, so the model is now downloaded and it's saved into the directory, and now this response is being generated by the model we have just downloaded, and it's replying to the query we have asked earlier, which was to download this model for us. Okay, so just ignore this response. Alright, let's just quit this R2 AI prompt now. Let me clear out the terminal once again. Okay, so now the model is downloaded and it has been set as a default model inside R2 AI prompt. Let's now deploy this model locally so that during our binary analysis, we can query this model from Radare2 terminal itself. And in order to make this work, we need to install one final plugin called R2 AI server. While there are various other options available for deploying an LLM model such as LM Studio, Olama, but since we are working within the Radare2's ecosystem, it makes sense to stick with Radare2 specific plugins for seamless integration. So again, by using r2pm-ci command, we are going to install this one final plugin R2 AI server. Enter. Alright, so this was the last one. I promise no more installations from here on. Okay, so now we have our model downloaded and we also have R2 AI server, which we are going to use to deploy the server locally. Let's now deploy our model by launching R2 AI server using r2pm command -r followed by the name of the plugin, which is R2 AI server -l R2 AI followed by -m, which is gonna tell which model to use. And if you remember from the installation, our model was downloaded under home ubuntu.local share R2 AI models directory, right? And under this we should have this granite model which we downloaded earlier. So let's paste it and hit enter. And if everything is set up correctly in your terminal, you should see this message saying serving at port 8080, which means that the model is now deployed locally and the server is listening on port 8080. So we can query this model by sending requests to this particular port. Now let's head back to this terminal where we have tested this authenticator binary, and let's now load it into Radare2 for further analysis. And in order to load it into Radare, we simply have to call R2 command followed by the binary name, which is authenticator in this case. Hit enter, and let's now perform a quick analysis on it using AAA command. Now let's see what all functions we have in this binary using AFL command. So these are all the functions which Radare has identified, and it looks like the binary is stripped because we don't have the function names available for the user defined functions, and we can only see some of these functions which are the imported ones coming from external libraries. Then we have this main function, which is generally the entry point for any binary, and this is usually the function which gets executed when we launch the binary. So let's seek to this function and see what's inside it using s command followed by the name of the method, which is main. Now you see our cursor has moved from this offset to this where main function is located in the binary, right? And now we can look at its disassembly using pd command, which stands for print disassembly. There we go. Okay, before looking into the disassembly, note that this is not an ARM64 binary but an x64 binary. So the instructions you see over here belongs to Intel's x86 architecture. Okay, let's quickly try to make some sense out of these instructions in order to figure out what's going on inside this main function. And don't worry if you don't understand anything by looking at this disassembly, because in the end we are going to leverage AI to do the heavy lifting of understanding these instructions for us. So understanding this assembly is not crucial, but it's always good to have a look at the disassembly. Alright, so at the top we have the function prologue, which is responsible for setting up the stack frame, right? Then here we have a load effective instruction, which is actually loading this string enter password into RSI register. And this is what we saw at the beginning, if you remember, when we executed the binary, right? Then we have this instruction move ABS RAX followed by a long hex value. And thanks to Radare2's advanced analysis functionality, it has automatically identified that this value is a string value which represents supersec. Okay, so what's happening over here is basically this string is going to be stored into this RAX register. Then we have another similar instruction move dword followed by a hex value. Again, by looking at the commands put by Radare2 analysis, this hex value translates to URE1. So this instruction basically is storing this string URE1 into a memory location pointed out by this address. Then if you follow along the same approach, you will find this instruction which is move EAX, hex 3332, which is again storing a string value into EAX register this time, and this hex value translates to 23 in string form. So basically, in short, these instructions are loading this string supersec your123 onto the stack, and the reason why it is splitted like this is because of the optimizations done by the compiler and memory alignment in assembly. So what we can do over here is, for readability purpose, we can put a comment using cc command. Then we want to put a comment in the form of a string. So we have identified that the string which is being stored over here is super secure 123, right? So it's super secure 123. And let's also mention the offset from where this string is being loaded. So this super secure string is being loaded from this offset. So let's copy this and paste it over here. Hit enter. Now let's again print out the disassembly using pd command. And this time, if you go back to this offset where super secure string is being loaded, you see our comment string super secure 123, right? So this now makes it more easy to understand what's happening over here. Then you can see that there are these functions print f standard input, f gets, strc, spn. So all these functions are the imported functions, right? But just by looking at these function calls, it's not clear yet what these functions are doing and what's the role of these imported functions over here. Okay, let's not go too much deep into these instructions because the end goal is to make use of AI to analyze all these instructions for us. Then we can see two interesting strings which are access denied and access granted, right? So if you remember, when we executed the binary, we got this access denied message and it's being loaded into this RDI register using load effective address instruction. Then using this puts function, most likely it's printing out this message onto the console which we saw earlier, okay? So when we enter the wrong password, most likely this piece of block will be executed, which is responsible for printing access denied error message on the console. Similarly, we have this access granted message followed by the puts function call. So again, using this put function call, we can say that this access granted string is being printed on the console when we enter the correct password. So as a reverse engineer or a security analyst, our goal here is to understand the logic behind how the program determines whether to print this access granted message or to print this access denied message. And we can see few comparison instructions over here, right? But it's not immediately clear what values are being compared with, right? Because the value with which the comparison is being made, it's not clear as of now. So at this point, you can see that without a solid understanding of assembly instructions, it becomes quite challenging to grasp the logic behind the program. So what other options do we have to figure out the logic of this program? Remember, we installed R2Ghidra plugin for decompiling the function, right? Let's put it to use. So this plugin R2Ghidra will attempt to convert all these assembly instructions into their equivalent high-level C code, making the logic easier to understand. So in Radare, we can simply call pdg command to get the decompile code. Hit enter. And there you have it. This is the equivalent C code which Ghidra's decompiler generated. It's important to note that all the traditional decompilers such as Ghidra, IDA, even Radare 2's default decompiler rely on heuristics and pattern matching to translate these assembly instructions into equivalent C code. However, this process is not always perfect. Sometimes the generated code can be unclear or difficult to understand. Additionally, traditional decompilers lack contextual awareness. What I meant by this is that they analyze the code at a syntactic level but do not understand the program's overall logic or intent. This means they cannot infer high level abstractions, variable names, or meaningful function roles beyond what is explicitly present in the assembly. As a result, we security researchers or reverse engineers often need to manually refine and analyze the output to fully understand the decompiled code. So as you can see here, the variable names are just some random values which does not make any sense, right? Similarly, the logic of the program is still not very clear, like which bytes or strings are being compared with in order to decide whether to print access denied message or to print access granted. However, it's somewhat easier to understand what's going on in the program by looking at these if else condition, right? Then we have some variable initialization being done over here. Then we have this printf statement call where this enter password string is being passed. Then we have fgets calls. So it's somewhat easy to understand as compared to the assembly over here, right? Okay, so still you have to put in a lot of effort to figure out what these variables are actually, what this logic is doing exactly, right? But let's see how AI can benefit us in this situation. So it's time to bring out the big guns. Let's finally leverage the AI model we have deployed over here. So we will use it to decompile this piece of code and see how well it translates the assembly into a more readable high-level representation as compared to the one which Ghidra decompiler gave us. For that, we have already installed Deck AI plugin, right? We have to configure it first before making use of it. So using deck AI-e command, we can see all the configurable variables which we need to configure. Right? Firstly, we have this API variable which by default sets to OLAMA. So because we are using R2 AI, let's just change the API from OLAMA to R2 AI, and for that we can simply execute deck AI-e, name of the variable which is API, and the value R2 AI. Enter. Then next variable is the host variable which is set to localhost. Since we have deployed the model locally on our system, there is no need to change it. However, if your model is hosted on a remote server or another machine, you will need to specify that machine's IP address over here. So this is one of the key advantages of using Deck AI plugin. It offers flexibility. If you don't have a powerful local machine to run the model, you can deploy it on a cloud server and access it remotely instead. Next, we have port variable which is currently set to 11434, but our model is deployed and listening on port 8080. So we have to change it using deck AI-e followed by the variable name which is port, and let's set it to 8080. Enter. Next, we have another interesting variable called prompt. This serves as a query that the model will use to process the information, and based on the content of this prompt, the model will analyze the input and generate the corresponding output. By default, the prompt is set to rewrite this function and respond only with code, no explanations, no markdown, change goto into if else for while, simplify as much as possible, use better variable names, take function arguments and strings from commands like string. By looking at this prompt, it looks like a solid starting point, but let's make a slight modification and let's also instruct the model to identify and remove any dead code if present. So for that, again, let's modify this prompt variable using deck AI-e command. Let me just copy paste this whole prompt because we just have to add one additional comment over here. Let's put it after this and say remove any dead code. Enter. Now you see the prompt, it's modified and we have just added this comment, remove any dead code. Okay. Then another interesting variable is this language, which is currently set to C. Based on this, the model will determine in which programming language the code should be decompiled. Currently it's set to C. Let's leave it as it is for now. You can obviously change it to any other high level programming language like Python, Java, Swift. Okay. Alright, so that's pretty much it. Let's just quickly review all the variables which we have set by again running decai-e command. And now we can see the API variable is changed, the port is changed, the prompt is modified, and that's it. So with this configuration, all that's left to do is call the decai plugin. And to do that, we simply need to run decai-d command. And now this process may take some time depending on the processing power of your machine. In the meantime, let me show you what's happening on the backend where the model is deployed. And as you can see, it received a GET request along with the prompt we set earlier, right? And also after the prompt, R2AI also added this command, transform this pseudocode into C, which is gonna tell the model to convert the pseudocode we have provided from Radare into C language. So now the model is basically analyzing and processing the code it received, and once it's done, it will return the result back over here in Radare terminal. Awesome. As you can see, the decompiled code looks much cleaner now and the logic is much clearer. The model has even assigned appropriate variable names based on the context. And remember, we instructed the model to remove any dead code. Well, it did just that, eliminating all the unnecessary junk and leaving us with only the core logic. However, it's not 100% correct. For example, in else condition, instead of stack check failed, it should have printed access denied error message, right? But still, even for a rookie, he or she can tell what's going on in the main function, right? And you can even use it to replicate the same functionality with small tweaks here and there. So it's clear now that the password which user is entering is being stored into this password variable with the help of a standard input through this fgets function. So whatever user is entering, that is going to be stored into this password variable, which is declared over here. And then in this if condition, we have this strcmp function call, which is responsible for comparing two strings. First one is the user entered password and another one is the hard-coded password, which we also saw during the static analysis of disassembly. So basically through this string compare function, it's comparing the user password, user entered password with this hard-coded string super secure 123, and if they match, it will print access granted message. Let me also show you how well our model did in generating this decompiled code by comparing it to the original source code. So let me open up another terminal, and over here you can see that we have this C file which contains the source code. So let me just print the contents of this file, enter, and you see over here at the top we have include stdio and string.h. That's exactly what model has also predicted, right? Then we have max length of 32 and then a function which is a useless function. So in this code I have deliberately added couple of functions which are basically doing nothing. They are just there to confuse and make reading the code difficult. For example, here if you see this if condition, this condition will never execute because the fake value is initialized with 1337 statically and it's not going to be modified anytime. And I am comparing it with 42, which means this condition will always be false, right? Similarly, this useless function is also being called based on this another if condition, which is again a useless condition which will never be true. Okay. And after all this bogus code, we have this enter password, which through fgets it's taking the input from the user via standard input stream. That's exactly what the model also predicted, printf, and via fgets, it's taking the user input, right? And now you can, and if you remember, we have explicitly asked the model to remove any dead code, right? And in the code, we have all this dead code present, which the model identified and removed it from the final decompiled code. How cool is that? And then let's come to the actual logic, which is this one: string compare, access granted, otherwise access denied. So the if condition is exactly what we have in the source code, right? It only messed up with the else condition. Instead of this stack check field, it should have printed access granted, but that's okay. With this decompile code, you can understand the actual core logic of the main function. So that's basically it, and this is how you can harness the power of AI to streamline and simplify the reverse engineering process. By using AI models, we can automatically clean up and clarify complex assembly code, making it much easier to understand and analyze. Subscribe, share, and like for more such interesting security insights.